Hello everyone, this is QED Math and I'm going to be covering the first 5 questions of the 2018 AIME 1. So this is problem number 1. Let S be the number of ordered pairs of A, B, 1 less than A, less than or equal to A, less than or equal to 100, B greater than or equal to 0, such that this quadratic polynomial can be factored into the product of two not necessarily distinct linear factors. And then we want to find the remainder when S is divided by 1,000. Okay, so it's saying that x squared plus ax plus b can be factored into linear factors with integer coefficients. Let's call the roots of the factoring alpha and beta. So this can be factored as x minus alpha plus beta. And now let's just use Vieta's rules to get coefficients in terms of the roots. So by Vieta, we know that alpha plus beta is equal to negative a and alpha beta is equal to b. From this, we can conclude that A is equal to negative alpha plus beta, and then B is equal to alpha beta. We're given that A is a positive integer, meaning that alpha plus beta must be negative. And then we're given B is a non-negative integer. So that means alpha and beta must both be negative in order for A to be a positive integer and B to be non-negative. So we can note that alpha beta is less than or equal to 0. And without loss of generality, let's assume that alpha is greater than or equal to beta. Because the roots will be in some ordering, let's just assume that we call the greater root alpha and the lesser root beta. And then now let's just perform a little casework. We discussed that alpha and beta must be less than or equal to 0. So let's first start if alpha is equal to 0. Then what can beta equal? Beta can't be 0 because that means A is equal to 0. So beta can be -1, which means A is equal to 1, -2, all the way until -99, and then -100. That's when A is equal to 100. And then this will produce a unique factorization for our quadratic polynomial. Let's go alpha is equal to -1. Alpha is equal to -1. Beta must be at least alpha. Alpha is greater than or equal to beta, so beta needs to start from -1, -2, all the way until -99. We want to make sure we have alpha plus beta is at least as -100, right? So next we have alpha is equal to -2. Beta can be anything from -2. I'll go a little bit quicker now to 98. Alpha is equal to -3. Beta can be anything from -3 to -97. Okay, now let's just see how many ordered roots we have so far. This gives us 100, this gives us 99, this gives us 97, this gives us 95. How I'm doing that is I'm just ignoring the negative and doing the last term minus the first term plus 1. So 97 minus 3 plus 1 would give us the 95, all the way until our very last case we have alpha is equal to -99. Yeah, alpha is equal to -99. Then beta, actually no, the very last case is when alpha is equal to -100. And in that case, beta is just 0. That doesn't make very much sense. Okay, so actually this is not the case. The very last case is when alpha is actually equal to -50. And in that case, beta is -50. And that'll just give us one solution. So we have the sum of the odd numbers and then plus 100 at the end. So let's just do this. This is a pretty routine calculation. This is just the sum of the odd numbers, which is just the number of terms squared. So that's 50 terms squared plus 100. Doing this gives us 2600. The problem wants us to find this, the remainder once divided by 1,000. So that would just be 600. Let's move on to the next problem. So the number n can be written in base 14 as ABC, base 15 as ACB, and base 6 as ACAC. where a is greater than 0. Find the base 10 representation of n. So n is equal to ABC base 14. Let's expand that. This is just 196a plus 14b plus c using the definition of a base n representation. N is equal to ACB base 15. This is equal to 225a plus 15c plus b. And finally, n is AC base 6. This is equal to, let's see, for a's, we have a 6 cubed a and we have a 6a. They'll form a 222a. And we have a 6 squared c and a c. That'll form a 37c. So, and then these are all equal. So let's form a set of equations. If we call these, this is 1, this is 2, this is 3, equating 1 and 2 and moving whatever's in 1 to whatever is in 2, we have 29a plus 14c minus 13b is equal to 0. And moving the terms in 2 to the terms in 3, we have, let's see, negative 3a plus 22c minus b is equal to 0. And finally, moving 1 to 3, we have not negative 6, it's actually 26. 26a minus 14b plus 36c is equal to 0. Okay, so this seems like a messy equation to solve, and I'm actually not going to solve this. The reason is, let me first notice something. Base 6, this is AC. This tells me that A and C are between 0 and pi inclusive. So now, since A and B are obviously integers, let me just perform some modular arithmetic. Let me take this equation mod 14. That'll give me A plus B is congruent to 0 mod 14. And let me just explain that a little bit further. 29a is 28a plus a. 28a will always be a multiple of 14, so that just becomes a mod 14. 14c is always a multiple of 14, and negative 13b is negative 14b plus b. The negative 14b goes away. So we have this equation, and then let's just play a little bit of guess and check. So a is equal to 0, b is equal to 14. Which equation? Let me just use this equation. That means 14c is equal to 13b minus 29a. 13 times 14 minus 29 times 0. That gives me, dividing both sides by 14, that gives me c is equal to 13. C must be less than or equal to 5, so we can reject that. 1, 13, 2, 12, 3, 11. The reason I can't go further than 14 exactly is because then b would be too large to be represented in base 14 and base 15. So if we have 1 and 13, 14c is equal to 13 times 13 minus 29. This is 140. C equals 10, again, too big. Let me just 410. If this is A of 2, B is 12, we have 14c is equal to 13 times 12 minus 29 times 2. This is 156 minus 58. That becomes 98. So c is equal to 7. Too big again. Next one will work, hopefully. Let's see. 14c is equal to 13 times 11 minus 29 times 3. This is equal to 143 minus 87. This is 56. C is equal to 4. So c equals 4. This works, but this may be an extraneous solution since we have to check it with the other solutions. If we do that, we get, if we plug it into whatever this is, we get negative 3 times 3 is negative 9, plus 22 times 4 is 88, and then minus 11. Yeah, that's definitely not equal to 0. So let's move on to this one. This one should work. Let's just find the corresponding c and make sure it works. So 14c would be equal to 13 times 10 minus 29 times 4. That's 130 minus 116. That's 14, so c is equal to 1. So we found a set of solutions. A is equal to 4, b is equal to 10, and c is equal to 1. Okay, so let's just see if this works. Plugging into the first one, we get negative 12 plus 22. That's 10. Minus 10 is 0, that works. 26 times 4 is 104. 104 minus 140 is negative 36, plus 36 is 0. So this is a perfect solution. So let's just find the base 10 representation. So we know this can be written as 4, 10, 1, base 14, right? Base 14. 10 is technically not a valid digit, so this would actually be 4a1 in base 14. And then let's just compute what this is, and we're done. So this would be 4 times 14 squared plus 10 times 14 plus 1. That's 196 times 4, which is 784. 784 plus 141. That's 925, and we are done with the second question. Okay, so for problem number 3, Kathy has 5 red cards and 5 green cards. She shuffles the 10 cards and lays out 5 cards, 5 of the cards in a row in random order. She will be happy if only if all red cards are adjacent and all the green cards laid out are adjacent. For example, these orderings are happy because there's basically no interruption between reds and greens. Reds flow, and then whenever green comes, the greens will flow too. And yeah, an example when she's not happy is given here. The G kind of interrupts the flow of the R's. The probability that Kathy will be happy is M over N. We want to find M plus N, blah, blah, blah. Okay, so without loss of generality, let's first suppose that one of the cards come out. It's red. It actually doesn't really matter because one of the cards will be red or green. And then from there, whatever is valid will just be an inverse of each other, as we'll see soon. So if the first is red, 4 more cards comes out the chute. Let's see what comes. So let's just list what will make her happy. We can have all R's, that's fine. We can have 3 R's followed by a G, that's fine. We can have RR and then G, but if G is going to interrupt now, we have to finish off with the G. And then we have R, G, G, G by similar logic, and we can have all G's. And now it just comes to finding the probability of this. This is not too bad. So an R comes out. So we have 4 R's left. So there's a 4/9 chance we'll choose one, and then a 3/8, and then a 2/7, and then a 1/6. For the next one, there's a 4/9, there's a 3/8, 2/7, and then a 5/6 chance. There are 5 green cards, 6 remaining cards. And then I'll probably do this without talking now. Similar logic. Okay, so now let's just compute. Everything has the same denominator, 9 times 8 times 7 times 6. So let's just compute the numerators. 4 times 3 times 2, that's 24. This is 4 times 3 times 2 times 5, which is 120. 4 times 3 times 5 times 4 is what, like 240? Yeah, 240. Next one, 4 times 5 times 4 times 3, that's just this in a different order, so that'll be 240 again. And then 5 times 4, that's 5 factorial, that's effectively 120 over 9 times 8 times 7 times 6. I won't go ahead and compute that. So let's just see. We have 120 here. That's another 240. So we have 720 plus 24. 744 over 9 times 8 times 7 times 6. Okay, first thing I want to do is I want to sum the digits of 744. 7 plus 4 plus 4 is 15. So we know this is divisible by 5. Divisible by 3. And then furthermore, 744 is even. So we know that this number is divisible by 6. So we can cancel some of the stuff. 744 divided by 6, that's 1614, 2, 12, 2, 4. That's 124. Hopefully I did that right. So 124 over 6 goes away. So we're left with 9 times 8 times 7. Next thing I want to notice is 124. Last 2 digits are 24. That's divisible. That means it's divisible by 4. So 124 divided by 4 should be 31. And then if I divide this by 4, that's just 9 times 2 times 7. That's 31 over 14, 126. 31 is prime, so this will be what it is in lowest terms, m over n. We want to find m plus n. Doing that gives us 157. Okay, next problem. So in triangle ABC, AB is equal to AC is equal to 10, BC is equal to 12, and point D lies strictly between A and B on AB, point E lies strictly between A and C on AC. Underline this, and we have this equality condition, and we want to find AD. Okay, draw, this is I can tell this is a isosceles triangle. This is ABC, AB is equal to AC is equal to 10, BC is equal to 12. D lies strictly between A and B, E lies strictly between A and C, such that AD is DE is EC. So maybe like AD, DE, EC. So these guys are all the same. Let's call them X. And we want to find AD. AD, so we want to find X. Okay, let me just fill out what I know. This is 12. And if this is X, this is 10 minus X, 10 minus X. That may be useful, that may not be. Okay, so the first thing I noticed here is that, let's look at this. This is an isosceles triangle over here. Now, cosine of A is actually easy to compute. We can solve cosine of A using this triangle, law of cosines, and we get something in terms of X. We can also use the big 10, 10, 12, 12 triangle and get cosine A is equal to some constant. Now, if we equate them, we get an expression, probably quadratic, in terms of X, and we can solve for X and we're done. So that's the game plan. Let's go for it. Cosine A, just memorize it. It's 10 squared plus 10 squared minus 12 squared over 2, 10, 10. Let's just quickly do this computation. That's 200 minus 144. That's 56. 56 over 200. We can divide by 4. No, we can divide by 8 even. That's 7 over 25. Now let's do cosine A on the smaller triangle. That's x squared plus 10 minus x squared. I'll write that as x minus 10 squared minus x squared over 2x 10 minus x. And then we know we should equate that in the future. So let's do that right now. Set up the equality. X squared's canceled, so we're left with x minus 10 squared. 2x 10 minus x is equal to 7 over 25. Let's cross multiply. So I believe it's 25x minus 10 squared is equal to 14x 10 minus x. That came from multiplying the 7 and 2. So now this looks quadratic, but what I can do is I can actually take out a negative, factor a negative from 10 minus x to make this an x minus 10. And x obviously does not equal to 10 because, not there, because we're given that they A and B lies, this is strictly in between A and B, so it must be less than 10. Not that. So it must be less than 10, so we can safely cancel out the x minus 10. 25x minus 10 is equal to negative 14x, and now it's just a matter of solving. 39x is equal to 250. That came from bringing the 14x over and bringing the negative 10 times 25 over. So x is equal to 250 over 39. Problem probably asked for m plus n or something. P over q, p plus q. Doing that gives us 289. And let's move on to our last problem. For each ordered pair, which is my favorite one out of the 5. So for each ordered pair of real numbers x, y, satisfying these two systems of equations, there's a real number k, such as this is true, and we want to find the product of all values of k. Okay, so first thing that caught my eye in this problem were the interesting bases, namely that one is the square of the other. So let's actually use some logarithm properties. So what I'll do is, this is our equation 1, log 2 of 2x plus y. I'll just maybe like list some properties on the side. Log AMBN is n over m log AB. So we can do that here. That's 2 squared. This is 2 squared. and then we can think of this being as to the power of 1. So this is 1/2 log 4 of x squared plus xy plus 7y squared. And then we can think of the next property, which is log base a of b to the n is equal to n log a b. We can use this property in converse. We have 1/2 log 4 x squared plus xy plus 7y squared. We can take this n up. So we get log 2 of root, well, x squared plus xy plus 7y squared to power 1/2, but that's the exact same thing as root. So let's go ahead and do that. Log 2 of root x squared plus xy plus 7y squared. And then 2. Exact same logic. I'll probably just do it stated directly now. Log 3 of 3x plus y is equal to log 3 of the root of 3x squared plus 4xy plus ky squared. Okay, so we have two logs with same bases. Let's just equate the terms. So 2x plus y, and I'll just do one better. I have a square root. Let me get rid of that. Let me square both sides. And then square both sides of this. 3x plus y squared is equal to 3x squared, 4xy, ky squared. Let's do some simplifying. Second equation, let's call, well, we have 1, 2, but whatever. Second equation won't be so useful so far since we have an unknown k. There'll be 3 unknowns, so it's probably not going to be helpful. Let's focus on the first one. So let's expand this. And then 4xy x squared. That's 7y squared. And I'm just going to focus on this for now. Bring everything to one side. Divide by 3. And then factor. Yeah. Okay, so this is kind of like a wishful thinking factorization. If you did not see that immediately, what you could have done is you could have let y equals kx. This is called homogenization. Since every term has a degree of 2, we can do this. We can cancel out the x's, and then we can have a quadratic in terms of k, and then we know those are factors. We'll get this as well. So we have 2 cases now from this factorization. Forgot to pull a 0. So now we have 2 cases. X is equal to y. And from here, let me use this formula over here. Let me expand this first. 9x squared, 6xy, y squared is equal to 3x squared, 4xy, ky squared. 6x squared plus 2xy plus 1 minus ky squared is equal to 0. And then let me just note that over here. Okay, the case when x equals y, we can plug this into this equation over here. Sure, we can just use x, so 8x squared plus 1 minus kx squared is equal to 0. In order for this to hold, we must have 1 minus k is equal to -8, so they can cancel. So k is equal to 9 in this case. And for the second case, that's when x equals -2y. I think it's easier to just replace x with -2y. So -2y squared is 4y squared. Let's just plug in what we have. 4y squared, 24y squared minus 4y squared plus 1 minus k y squared is equal to 0. 20y squared plus 1 minus ky squared is equal to 0. 1 minus k, therefore, is equal to -20. K is equal to 21. So we have k is equal to 21, k is equal to 9. Problem asks for the product of all possible values of k. That's 189. And we are done. Thank you for watching this video. So the AIME is coming up in 1 month, so I'll definitely release more from the 2018 AIME and probably other AIMEs as well. Take care. I'll see you guys in the next video.